Okay, here we are with a question which is all about ideal gases. Okay, we're looking at a sample which is kept at a constant volume. We've got a graph and we want to know what's the volume of the gas. Feel free to have a go, and then when you're ready to see an explanation, hit play. Okay, so we've got a nice straight line graph here, and that's something that's got to be important. And we want to know the volume. Now for this, we should always refer back to our ideal gas equation. Now in this case, we're going to use this version, PV equal to nRT. Obviously, there's PV equal to nKT available. However, we're looking at moles, and so therefore we're going to use this version. And what I'd suggest you do in this case is to have a little think about comparing this equation to the graph. We've got P on the y-axis, so I'm going to rearrange this for P. I've used my colors here just to highlight a few things. We've got P on the y-axis, T on the x-axis, and then NR over V. Why have I done that? Well, you notice here, this is in exactly the same form as a straight line with the form y equal to mx. Okay, we've got y is equal to p, t equals x, and then this bit here. In other words, what this means is the gradient of my graph is going to be equal to nr over v. So, if the gradient is, well, so good I've done it twice, gradient is equal to nrv, that means that if we take our gradient value, we're going to have delta p over delta t. So delta p over delta t is equal to nr over v. If we rearrange that, then we're going to have v is equal to nr times delta t over delta p, in which case the answer here is A. Now I'm sure there's a way you could do this with dimensional analysis as well, which would show that you need to have temperature on the top and pressure on the bottom. However, the key one to get away from is these ones here at the bottom, which take the ratios individually.